Section 1.4 in college algebra is going to cover solving some interesting equations. We're going to start out with radical equations. What we want to do first when we are solving equations that have radicals in them is we want to isolate the radical. Now, as you're going to see, sometimes there's more than one radical. When that happens, a couple of things are possible. We'll get to see some of the most interesting ones together. Then you're going to raise both sides to the power in the index. So the index is that little number that's inside the elbow of the radical. So this one is an index of 3. When there's not an index written, it's a square root, so the index is 2. Then you're going to check, well, you're going to raise one and then you're going to solve that equation. Then you're going to check by subbing the solutions into the original equation. If the original power was even. I mean, you can skip that step if you want to, but you have a chance of actually having the right answer and getting it counted wrong because it was like one of them was supposed to be X'd out. So let's see. The first thing we're going to do here is isolate the radicals. So we will be, radicals already isolated, never mind. So then we're on to the next side, raise both sides to the power of the index. So we're going to cube the left side, cube the right side. Now when we cube a cube root, what ends up happening is that the cube root and the cube are opposite operations. So they kind of negate each other and just end up leaving you with the argument of the radical or the radicand. So we're going to be left with 4 minus 6x on the left side. And then we're going to do 2 cubed. So 2 times 2 times 2, which is 8. Then we just go through and solve. So subtract 4, subtract 4. We get negative 6x equals 4 divided by negative 6, divided by negative 6. And we get x equals negative 4/6 or negative 2/3 because we'd want to simplify that. Do we need to check that one? No, we do not, because the power was odd originally. It was cube root, so we're good with not checking. Okay, on to the next one. We have x plus 2 square roots of x minus 7 equals 10. So we're going to start by working to isolate the radical. So I will subtract that x from both sides, and that's going to leave me 2 square roots of x minus 7 equals 10 minus x. Now, my radical's not isolated, but if I divide this side by 2 to get my radical by itself, the 10 is fine. I would get 5, but then I would have x over 2, which is a fraction, and we usually would rather not deal with fractions if we can help it. So I will just show you this little easier way to deal with it. If you have a number out in front of your radical and you square it, what's going to end up happening is squaring the radical is going to get rid of the radical, so it just leaves the parenthesis. But then we also have to square the number, so we'll end up with the number squared times the radicand. That's a handy thing to keep in mind. So when I square both sides of this problem, I'm going to have 2 squared, so I'll have 4, and then times x minus 7 equals, Now on the right side, it's not going to be 100 minus x squared. I have to remember to FOIL that. So it's like 10 minus x times 10 minus x. And I have to FOIL that out. So I'll do 10 times 10, 100, 10 times negative x minus 10x, negative x times 10 minus 10x again, negative x times negative x plus x squared. I'll go ahead and distribute this 4, combine my like terms. So I've got 4x minus 28.
Can we have a custodian in front of the media center to take 2 tables away?
Equals 100 minus 20x plus x squared. And then this is a quadratic formula, or excuse me, a quadratic equation. So I am going to make it equal to 0 to start with. So I'll subtract my 4x over and add my 28. And I'm going to go ahead and put it in standard form as I do that. So I'll put my x squared first, and then minus 24x, and then plus 128. Now at this point, excuse me, you could factor this quadratic formula, complete the square. However you feel like solving that quadratic equation, I'm going to factor it. It'll be x minus 8 times x minus 16. I'm cheating. I've already done this problem. So then when I solve, I get x equals 8 or x equals 16. Now, do I have to check these? Yes. Yes, I do. Because my original index was even, I have to check it. So I'm going to end up replacing these x's in the original equation with 8, and then do it again, replace it with 16. So I will check these. So I will have 8 plus 2 square roots of 8 minus 7 equals 10. Then I just work through this left side. So that's 8 plus 2 square roots of 1. That's 8 plus 2 times 1, which is 2. And that does equal 10. So x equals 8 works out. And I check this one. I have 16 plus 2 times square root of 16 minus 7 equals 10. So that's 16 plus 2 square roots of 9, which is 16 plus 6, which does not equal 10. So x equals 16 does not work. It's what we call extraneous. But x equals 8 is a valid solution to that equation. Okay. Kind of got out of my bounds here. Let's get you separated here. Okay. Next one, radical equation. Oh gosh, this one has 2 radicals. So what we're going to do is isolate one of the radicals and go from there in solving. So we'll move one guy over to the other side. So we have square root of x plus 1 equals 3 minus square root of x minus 4. So now at this point, we are going to square both sides. So here I've got squaring that radical, which is going to be easy peasy, lemon squeezy. Squaring the other side is difficult, difficult, lemon difficult. So on the left side, we have just x plus 1, but on the right-hand side, we have a foiling situation. It looks like it's going to be real difficult. I mean, it kind of is. Just don't get lost in the weeds on it. I'll step you through it. We're going to be fine. So we are going to FOIL this guy. So we're going to keep our x plus 1 over here. Then we're going to do FOILing. So first times first. That one's easy. It is 9. Outside times outside. We've got 3 times negative square root of x minus 4. That comes out to be negative 3 square root of x minus 4. Then inside times inside. 3 times negative square root of x minus 4 again becomes negative 3 square root of x minus 4. And then last times last, we have a negative number times a negative number, which makes a positive number. And then I'm taking square root of x minus 4 times square root of x minus 4. That's the same thing as squaring it. So what that's going to do is take the radical off. And I'm left with plus x plus 4 without any radical. Now let's get on combining like terms. So these guys are like terms. And then the 9 and the negative 4 are like terms. So I'm going to go with x plus 1 equals negative 6 square roots of x minus 4. And then plus 9 minus 4 is 5. And then plus x. So now we're back to an equation with a radical. So we need to isolate the radical again. So I'm going to leave my negative 6 square root of x minus 4 on this side. I'm going to subtract my 5 and subtract my x on both sides. So that's actually going to just leave me with a nice negative 4 over here. Now, again, I could divide both sides by negative 6, but that's going to result in some fraction action. So I think what I'm going to do is go ahead and just square both sides as it stands. And then on the left side, that's going to give me 16. On the right side, that's going to give me, remember I have to square the number out front, so 36, and then get rid of the radical, x minus 4. Now it's looking manageable. Distribute that 36. So 16 equals 36x minus 144. Add that back over. What is that? 160 equals 36x. Divide by 36. And we get x equals 160 over 36, which those are both divisible by 6, question mark, by 4, because that would be 40, and 36 divided by 4 would be 9. Okay, so that's what we're getting for x, 40 over 9. Biscuits. Do we have to check this thing? Yes. Yes, we do. Because our original degree was even, we have to check that solution. So we'll do square root of 40 over 9 plus 1 plus square root of 40 over 9 minus 4 equals 3. So remember that 1 is the same thing as 9 over 9, which makes 4 the same thing as 36 over 9. Oh, yeah, times 9 times 9, 36 over 9. So then this becomes the square root of 49 over 9 plus 9 over 9. So 49 over 9 plus the square root of 40 ninths minus 36 ninths would be 4 ninths equals 3. Square root of 49 over 9 is the same thing as square root of 49 over square root of 9. So 7 thirds plus square root of 4 ninths is 2 thirds equals 3. 7 thirds plus 2 thirds is 9 thirds, which does equal 3. So that checks out. Let's see what's next. I'm almost scared to turn the page after all those fractions. Oh gosh, it's that quadratic in form stuff with the u substitution that I was talking about last time. So with a quadratic equation, we had ax squared plus bx plus c equals 0. And in the quadratic formula, it was this x that we used for x equals opposite b plus or minus square root b squared minus 4ac divided by 2a. With quadratic in form, it's not going to be x equals it's going to be something else equals. Like we've already seen this one here where it was x squared equaled opposite b plus or minus square root. So all of these problems, you're going to have one of your exponents be twice as big as the other. So like on this one, the exponent was 1, and this exponent was twice as big, x squared. On this one, the exponent is 2. On this one, the exponent is twice as big, so 4. So what we're going to do is we're going to rewrite all of our problems when we do u substitution. They're all going to be rewritten as a times u squared plus b times u plus c equals 0. We just have to figure out what u and u squared are. But it is always, always, always going to be the u is going to be the thing that is the lower exponent. The u squared is going to be twice as big. So let's work through some of these. Like let's just rewrite some of these, and then we'll do an example down at the bottom of the page. So we're looking for the exponent that is the smaller. This one's twice as big. So this is what our u is going to be. So we're going to replace x squared with u, and we're going to replace x to the 4th with u squared. Okay, next one. If you look at our exponents, this one's x cubed, x to the 6th. This is the one that's the smaller. That one's twice as big. So u is going to be x cubed. U squared is going to be x to the 6th. The next one has stuff in it. Stuff to the 1st power, stuff to the 2nd power. Whatever that stuff is, that's what we're going to replace with the letter u. And u squared is going to replace stuff squared. What's our next one look like? These are all the same way to represent, like different ways to represent the same thing, rather. A times 1 over x squared plus b times 1 over x is the same as a times 1 over x squared plus b times 1 over x, which is the same thing as a over x squared plus b over x, which is the same thing as a x to the negative 2 plus bx to the negative 1. Because remember, those negative exponents meant that the base was in the denominator just a second ago, but now we moved it up and it became negative. When we move it up, it became negative. So these are all the same. Our values for u are going to be found in that same location. So there's going to be different ways to write the basically same problem. So here, this is our guy. Here, this is our guy. This guy is a weird one. Here, this is our guy. I would use this one like one of these two. So on both of these, I would say that u is 1 over x and u squared is either 1 over x squared or 1 over x squared. We'd replace either of those with u squared. In this one, u is going to be x to the negative 1. U squared is twice as big, x to the negative 2. These two are the same, ax plus b square root of x and ax plus bx to the 1/2. Notice that the exponent of 1 is twice as big as the exponent of 1/2. That square root means a power of 1/2. So in this case, this is going to be our u value. So u is going to be either square root of x or x to the 1/2. U squared is going to replace the x. Same thing if I have a cube right here. This to the 1/3 means a cube root. To the 2/3 is twice as big. So we would replace this with x to the 1/3 gets replaced with u. X to the 2/3 gets replaced with u squared. So you're going to want to keep like this kind of sheet as reference as when you're starting to solve these problems. We'll do an example here and another example on the next page. So First things first, you want to get it equal to 0 before you start. So I am going to, I always want my leading coefficient to be positive. So I'm unfortunately going to move 2 terms over to this side. So now I have x to the 6th minus 2x cubed minus 3 equals 0. And then I'm looking at my exponents. I want to find the one that's twice as big, and I'm going to replace it with u squared, and the one that is not twice as big, the one that's regular, is going to be u. So in here I see 6 is twice as big as 3, which means I'm going to be replacing this x cubed is going to be replaced with u, and this x to the 6th is going to be replaced with u squared. So now I'm literally just rewriting my equation as u squared minus 2u minus 3 equals 0. So notice that I kept my coefficient, negative 2 stayed with the u, and the x to the 6 didn't have a coefficient, so it just got straight replaced with u squared. Now this little guy can be factored. So I can factor this and solve. It would be u minus 3 times u plus 1. So I get u equals 3 and u equals negative 1. Now, that is not what the problem wants to know. The problem doesn't want to know what does u equal. The problem wants to know what does x equal. So now I resubstitute what I had replaced before. So remember, before I took the x cubed out and replaced it with a u. Now I'm taking the u out and replacing with an x cubed. So x cubed equals 3. Same thing here. X cubed equals negative 1. And I have to solve these two equations to get what x is. So to solve x cubed, I take the cube root of both sides. So that gives me x equals cube root of 3. There's no plus or minus because it wasn't a square root, so it's just cube root of 3. And then cube root this side, cube root this side. Oops, the light's turned off. Then we need to take the cube root of negative 1, and I will tell you that it is negative 1. The cube root of negative 1 is negative 1. So when you have a cube root with a negative, essentially the negative just goes out front. So those are my two solutions. I don't need to check them. I can just go with it. Okay, here's one of those guys that's like stuff, right? So I have this stuff is to the first power, this stuff is to the second power. So remember that my u is going to be the lower of the powers. The u squared is going to be the one that is twice as big. So I'm going to replace this whole thing with a u and this whole thing with a u squared. I guess I could have replaced the whole parenthesis. So then when I rewrite my equation, it's going to be u squared plus, don't forget the coefficient, 4u plus 3 equals 0. Then I can solve this. I can actually factor it. That becomes u plus 3 times u plus 1 equals 0. So I get u equals negative 3, u equals negative 1. Now remember that they don't want to know what u is. They want to know what x is. So I'm going to go back and replace these u's with what I had initially replaced in the first place. So this is going to be x plus 1 over x equals negative 3. X plus 1 over x equals negative 1. And then I solve both of those equations. So I will multiply both sides by x. That gives me x plus 1 equals negative 3x. and then subtract x from both sides. So 1 equals negative 4x. So then x would be negative 1/4 by that one. And then kind of doing the same steps on the other. Multiply by x. X plus 1 equals negative x. Subtract x. 1 equals negative 2x. So x would equal negative 1/2. Now, hopefully, as I was starting out this problem, you were thinking to yourself, gosh, I see a variable in that denominator. I better think about my domain. Since I'm solving an equation and I have a variable in the denominator, the strategy I use to find my restrictions is to set the denominator not equal to 0. So in both of these cases, the denominator is x. So I set that not equal to 0, and that's my domain restriction. So when I check my solution against my domain restriction, neither one was 0, so both of these are valid solutions. Solving by factoring when we are factoring by grouping. Okay, factor by grouping. You actually, if you can factor AC method, you can factor grouping, because it's literally just taking the first two terms and putting them in a group, because we got 4 terms, taking the second 2 terms, putting them in a group, looking for a GCF. Here I've got x squared in common, so I can take x squared, that would leave x plus 4. Then when you look at the second group, remember if it starts out with a negative number, we have to factor out a negative number. In this case, the only thing I can factor out is negative 1. So I'll go minus 1 times x plus 4. Remember, factoring out a negative changes both of those signs. Equals 0. Then remember, one of our groups is that common parenthesis, x plus 4. The other parenthesis is going to be those GCFs, x squared minus 1. Now they want me to solve by factoring, so I'm going to have to keep factoring this guy, which is difference of squares. So now I have x plus 4 in that parenthesis, and then this one factors to x plus 1, x minus 1. Solving each of those gives me x equals negative 4, x equals negative 1, x equals positive 1. And those are my 3 answers. Oh boy, weirdly factorable. And I mean, like, this is weird. Weird. Weird, weird. So I have 3x times, parentheses, x squared plus 2x to the 1/2 minus 2 times x squared plus 2x to the 3/2 equals 0. So our strategy is going to be that we will factor out the GCF, which is going to be whichever parenthesis has the lowest power. We will then subtract that power from each exponent. Okay, so in this problem, our lowest exponent is 1/2. So I am going to factor out x squared plus 2x to the 1/2 as my GCF. So I'm going to take x squared plus 2x to the 1/2. That's going to be my GCF. Then I'm going to subtract that 1/2 from both of those exponents. And then whatever's left, I'm going to keep writing down. So here I go. I am left with a 3x here. And then when I do 1/2 minus 1/2, that's 0. That means this whole thing is gone. So the only thing I have in that spot is 3x. Okay, keeping on going. Minus 2. 3/2 minus 1/2 is 1. So that leaves me x squared plus 2x to the first power. And then I still have equals 0. Okay. What next? I'm going to go ahead and distribute my negative 2. So now I have x squared plus 2x to the 1/2 times 3x minus 2x squared minus 4x equals 0. Combine like terms. So we got x squared plus 2x to the 1/2 times negative 2x squared minus x equals 0. Now I'm going to work on factoring what's in this second parenthesis here. I see that I have a GCF. Both terms have an x, but remember when we started with a negative, we have to factor out a negative. So I've got my GCF from the first part that we worked on, then my GCF of negative x, and then what's left in there. So negative 2 divided by negative 2x squared divided by negative x is positive 2x. Negative x divided by negative x is plus 1 equals 0. Okay. Now we can solve because I have this times this times this equals 0. So remember that the power of 1/2, what that really means is it's a square root. So we had square root of x squared plus 2x equals 0. We have negative x equals 0, and we have 2x plus 1 equals 0. So when we solve each of those, this first one, I'll square both sides. So that gives me x squared plus 2x equals 0. Now to keep solving that, I am going to have to factor out a GCF, which is x. So I have x times x plus 2 equals 0, which gives me x equals 0, x equals negative 2. Negative x equals 0 also gives me x equals 0 if I divide both sides by negative 1. And 2x plus 1 equals 0 gives me x equals negative 1/2. Okay, I know what you're thinking. The original problem has a square root in it, so we have a domain restriction. I'm sure that's what you were thinking. Do we have domain issues? Yes. The original problem had a square root. Where, you ask? Because the power of 1/2 is the same thing as a square root. So that x squared plus 2x to the 1/2 is the same as the square root of x squared plus 2x. So basically remember that you can't have a negative number inside the radical. We're not really ready to directly solve this domain, but what we can do is check our solutions. So if we check x equals 0, x equals negative 2, x equals negative 1/2, we know that we can't have a negative number underneath there. So we want to check to make sure that x squared plus 2x can't be negative. So let's check that. So we got 0 squared plus 2 times 0, which is 0. So that one's okay. Negative 2 squared plus 2 times negative 2. That's 4 minus 4, which is 0. That's okay. Negative 1/2. So negative 1/2 squared plus 2 times negative 1/2. Negative 1/2 squared would be negative 1 times negative 1, which is 1. 2 times 2 is 4. And then 2 times negative 1/2 is negative 1, which gives me negative 3/4. That is not okay. So this x equals negative 1/2 is extraneous. So we only really have the two solutions of x equals 0 and x equals negative 2. Let's do another of those weirdly factorable ones, and then I'll let you go for a while. So we've got 2 times the parenthesis to the 7/3 minus the parenthesis to the 4/3 minus the parenthesis to the 1/3. So hopefully we remember from a moment ago that we are going to factor out the GCF that is going to be the parenthesis to the lowest power we have in our problem. 7/3, 4/3, 1/3. So 1/3 is our lowest power. And then that's going to leave us a bunch of stuff in there. I'm going to give it a square bracket this time because I feel like there's going to be more. So I have to subtract 1/3 from each exponent. So that is going to be my new exponent when I get on to the next line. Okay. The 2 is going to stay from here. And then I'm going to have x minus 4 to the power of 7/3 minus 1/3 is 6/3, which is 2. So 2 times x minus 4 squared. Minus 4/3 minus 1/3 is 3/3, which is 1. So minus x minus 4 to the first power, and then minus 1/3 minus 1/3 is 0. I don't know if you remember this or not, but with some exclusions later in calculus, anything raised up to the 0 power is going to equal 1. So when I replace this x minus 4 to the 0 power, I'm replacing it with 1 and then equals 0. What are we going to do with this mess? I mean, we could do u substitution in here if we wanted to, or we could FOIL that out and combine stuff. I don't know what you are thinking you want to do here. Are you thinking you want to FOIL this? I mean, I can't really hear you because, you know, you're there and I'm here and it's a different day. So I guess we'll FOIL. So that's going to be, when I FOIL that, x times x, x squared, negative 4 times x, minus 4x, another minus 4x, and then a plus 16. And then if I distribute that 2 onto that, that'll be 2x squared minus 8x plus 32. And then distribute this negative onto here, minus x plus 4, and then I still have minus 1. Then I should probably combine the like terms in here. So I got the negative x's and the negative x, the 32, the 4, and the 1. So now I'm at x minus 4 to the 1/3 times 2x squared minus 17x plus 35 equals 0. But wait, there's more, because we still have to factor what's in here. So we're going to use the AC method. So remember, the first thing to do is check and see, is there a GCF for all three of those? No, there is not. So I take the first thing times the third thing. So I got 70x squared, and I'm looking to rewrite this negative 17x. Looks like, let's see, when I multiply to get positive 70, that could either be like positive 7, positive 10, or negative 7, negative 10. In this case, if I do negative 10x, negative 7x, that's going to multiply to give me positive 70, but add to give me negative 17. So I'm looking at 2x squared minus 10x minus 7x plus 35. Get this group together. I can take out 2x and I'll be left with x minus 5. Get this group together, leads off negative, so I have to take out negative 7 times x minus 5. So back to the problem, x minus 4 to the 1/3 times the common parenthesis x minus 5 times the GCF's 2x minus 7 equals 0. Holy cow. Okay, now we're ready to solve. So We set each of these equal to 0. That gives us x minus 4. Remember, that means the cube root of x minus 4. So we can cube both sides, which basically just leaves us x minus 4 equals 0. So we get x equals 4 from that. From this one, we get x equals 5. From this one, 2x minus 7 equals 0. We get 2x equals 7. So x equals 7 halves. Okay, question. Do we have any domain concerns that would make us have to check? Remember that as of right now, our domain concerns are variables inside even index radicals or variables in the denominator. What we have in our original problem, by the way, the index of the radical is in the denominator. So that's a cube root, that's a cube root, that's a cube root. So do we have domain concerns? No. So we do not need to check those. All three of these values will be valid solutions, and we are out.